All right, so this problem says that cyclopropane rearranges to form propene according to the following reaction. We have the chemical equation given right here, and it says that the reaction is first order with a rate constant of 3.36 times 10 to the minus 5 inverse seconds at 720 kelvins. And if the initial cyclopropane concentration is 0.0445 molar, then what is the concentration of cyclopropane after 235.0 minutes? So as you can probably figure out from the title of this video, we're going to be using the integrated rate law to solve this problem. So the first step is to figure out which integrated rate law equation we are going to use. Each order of reaction has its own unique integrated rate law equation. Now the problem clearly tells us that this is a first order reaction, so therefore we are going to use the first order integrated rate law equation, which, if you recall, is the following, where we have the natural logarithm of the concentration of the reactant. I'm just going to call it A because that's the notation that we're familiar with. Natural log of the concentration of the reactant at time t is equal to minus AT, where K is the rate constant and T is the time, plus the natural logarithm of the initial reactant concentration, or concentration of A sub 0. So this is the equation that we're going to be used. So what we need to do is we need to identify what all of our known values are, and then we need to algebraically solve for our unknown value, right? Let's identify all of our knowns, right? So it tells us that the rate constant, K, is 3.36 times 10 to the minus 5, and that's inverse seconds. It also tells us that the initial concentration, or we're going to call it concentration of A sub 0, is equal to 0.0445 molar. And it gives us the time, right? T. That is going to be 235.0 minutes. Now, one thing that is immediately jumping out to me is that our time is given in minutes, but our rate constant is given in inverse seconds. And if you see here, the rate constant is multiplied by the time. So in order for the units to cancel properly, we need to convert our time in minutes to a unit that is compatible with our rate constant, which is seconds. So we have 235 minutes. We need to convert that to seconds. So I'm going to set up a simple conversion factor here, where I put minutes on the bottom. I'm going to put seconds on the top. Of course, there are 60 seconds in 1 minute. I'm going to cancel my minutes out. And what I'm going to be left with is 235 times 60, which is, I'm going to type it in my calculator real quick, 235 times 60. I got 14,100 seconds. I need to get rid of that there. Okay, 14,100 seconds. So that is our time. So what I'm going to do is I'm just going to erase all this conversion factor stuff just so that I can keep this very compact here. Take value and sort of bring it over here. Okay, so what do we know? What do we not know, right? Well, we know the rate constant, that's given. We know the time, that was given. And we know the initial concentration, that was also given. The only thing we don't know is the concentration after that 235 minute or 14,100 second interval of time, right? So that's what we need to do. We need to solve for this term here, concentration of A sub T. So we have the natural log of it, so we need to be able to get rid of that logarithm. And whenever you need to get rid of a logarithm, what you need to do is you need to raise the base of that logarithm to the power of the logarithm. And the base of the natural logarithm is called E, also called Euler's number. So somewhere in your scientific calculator, there's a button. This is like my calculator button here. And it looks like this, where you have e to the x. So the way that works is you punch that e to the x button in your calculator, and whatever you type within that expression after that e to the x entry, whatever you type in after that, it's going to raise that to the power. It's going to raise e to the power of whatever you type in after you type it that e to the x button, right? So in other words, we need to raise e to the power of both sides of this equation to get this natural log, or to get this concentration of A at time t all by itself. So what is that going to look like? Well, if I take e to the ln of A sub t, that's just going to be concentration of A sub t, right? So that gets this all by itself, right? And then we're also going to be left with e to this whole thing up here, right? Where we have minus kt plus the natural logarithm of the initial reactant concentration, right? So this whole thing is what we're going to be raising e to the power of, right? And so now we can just simply start substituting our actual numerical values for K and initial concentration and time, where all of the variables here sort of belong, right? And so I'm going to try to do this in a nice compact way here. So it's going to be, right, minus KT, right? So I'll go ahead and just make this like a bracket up here. So minus KT, so that's going to be the negative product of K, which is the 3.36 times 10 to the minus 5 inverse seconds, times the time, which is 14,100 seconds, right? Plus the natural logarithm of the initial concentrations, that's 0.0445 molar. And it looks like I'm kind of running off the page here, so I'll see if I can just drag this over here, give myself just a little bit extra room. I think that'll do it. So the initial reactant concentration, that is 0.0445 molar, right? So I need to raise e to the power of this whole expression over here. So that might seem like a pretty daunting task, but if you have the right scientific calculator, you can actually do this calculation quite easily. This is the scientific calculator that I use. It's called the TI-30X2S. If you like, I can provide a link to where you can find one in the description. I think they're on Amazon. What I really like about this calculator is that you can type this whole expression all on one line. You don't have to type just part of it and then write it down and then include that with whatever you need to calculate in the future. You can literally type this whole thing, e to the negative product of 3.36 times 10 to the minus 5 and 14,100 plus the natural log of 0.0445. You can type that entire thing all on one line. You can scroll back, you can look at your entries, and it'll remember your last, I don't know how many entries, but it'll actually remember your entries so that you can just scroll up and look at what you've typed and substitute things accordingly. So I'm going to go ahead and perform this calculation in my calculator. At this point, I would encourage you to pause the video and see if you can perform this calculation for yourself, and we can see if you got the same thing that I did. So here we go. Okay, and the value that I got was 0.0277 molar. Okay, so really the tricky part of this calculation was mostly algebra. It really doesn't have much to do with chemistry, but the chemistry part of it is just understanding which integrated rate law equation you have to use, and then the rest of it is just algebra. So we're going to move on to another problem, which I'll paste on the board here. All right, so this problem tells us that we have a reaction in which a single reactant decomposes, and it has a rate constant of 4.7 times 10 to the minus 7 inverse molar inverse seconds. And it says that if the initial concentration is 0.922 molar, then how long will it take for the reactant concentration to decrease to 0.016 molar? So this is another problem in which we're going to use the integrated rate law to solve it. So just like in the last example, the first step is to identify the order of reaction. That's going to tell us which integrated rate law equation we're going to use. And it's a little bit tricky because it doesn't tell us whether it's zero, first, or second order. So how are we going to solve this if we don't know the order of the reaction? If the problem isn't telling us, then how are we going to solve it? And the answer is to take a look at the units of the rate constant. So remember, each order of reaction not only has its own characteristic integrated rate law equation, but it also has its own characteristic units for K, the rate constant. And molar to the minus 1, seconds to the minus 1 is characteristic to which order? That actually happens to be second order. So the units of the rate constant, that's what tips you off that we're dealing with a second order reaction. So we're going to use the second order integrated rate law equation, which, if you recall, is 1 over the concentration of the reactant at time t is equal to positive KT plus 1 over the initial reactant concentration, right? And according to the problem, it says we have K, right? K is 4.7 times 10 to the minus 7, and that's inverse molar, inverse seconds. What else do we have? We have the initial concentration. We have concentration of A sub 0, which is 0.922 molar. And it also gives us the concentration of A at time t, which is 0.016 molar, 0.016 molar, right? So we have rate constant, we have initial concentration, we have final concentration. The only thing that we're missing is the time, right? So that's what we need to solve for. So we're just going to algebraically manipulate this equation to isolate the time, have it all by itself over there. And then we can just simply plug in the values that we know to solve for our unknown, right? So the first thing that we'll do is we'll go ahead and subtract both sides of the equation by this 1 over the initial concentration term, and that's going to result in the following equation where we have KT is equal to 1 over the reactant concentration at time t minus 1 over the initial reactant concentration, right? All I've done here is just, with this equation, I've just subtracted the 1 over the initial concentration from both sides of it, right? And then at this point, all I need to do to get that time all by itself is to divide both sides of this equation by K, the rate constant, right? So I'll go ahead and divide both sides of that equation by K. So that's going to give us T over here, and that's going to give us this whole thing divided by K, right? And so now at this point, it's just a matter of plugging in our numbers. So 1 over concentration of A at time t, that's going to be 1 over, what is that according to the problem? That's 0.016 molar. Initial concentration over here, we're going to plug in that value. That's, what is that? 0.922 molar. And then finally, our K value over here in the denominator of this whole thing is going to be 4.7 times 10 to the minus 7 inverse molar, inverse seconds. So again, if you're using a calculator like mine, which I highly recommend, this isn't the only calculator that can do this. There's plenty of calculators that can where you can enter this entire expression all on one line. But I highly recommend that you get your hands on one because it'll make you very, very quick at doing these. So if you're going to be tested on it, you can do it very quickly, and you can go back and check your work to make sure you didn't make any mistakes or anything like that. So I'm going to go ahead and put this into my calculator. And again, I'd encourage you to pause the video and bang out the calculation for yourself. See if you got the same thing that I got. Okay, here we go. Okay, I ended up getting a very large number. I ended up getting 1.3 times 10 to the 8 seconds. So it's a very, very long period of time, at least in seconds. Now, if you wanted to convert that to minutes or even hours to make your number a little bit smaller and more manageable, of course, you'd be more than welcome to do that. But at this point, it doesn't actually ask us to report the time in minutes or hours. And so technically, we could leave the answer just as it is right here, 1.3 times 10 to the 8 seconds, and consider ourselves content that we solved the problem. All right, guys, so I hope this video was helpful. If this video has provided value to you, I would highly appreciate your support in the form of a thumbs up on this video, and consider subscribing. I've recently noticed that about 98% of the time spent watching my content is by people who aren't subscribed, so chances are you're not subscribed. So I would love to have you on board. We're publishing content like this all the time, and I also stream weekly. Usually it's Sundays at 9:00 p.m. Eastern. So, all right, thanks again for watching. Love you guys, and I'll talk to you soon. Okay, bye.